Two graphics cards. One is 5 years old and has 12 GB of memory. The other is newer, has 16 GB, and costs 60% more. On the same model, the same test, the same settings, the old cheap one writes text faster, 42 tokens a second against 34. The newer card has more computing power. It just has less memory bandwidth, 288 GB a second against 360. That is the whole trick. When a model writes you a sentence, it is barely doing arithmetic. It is reading, and reading is bounded by memory. 5 things decide whether local AI works on your machine. 4 of them are not printed on the box you have been comparing. How fast your memory is, how many bytes get read per token, whether the thing fits, how much context you ask for, and what you are actually running it for. Get those right, and a $250 card beats a $4,000 one at your job. Get them wrong, and you spend $2,000 to run something worse than a free API. So, number 1, memory bandwidth, and why the number on every spec sheet turns out to be the wrong one. Here is what generation physically is. To produce 1 token, the machine reads every weight in the model out of memory and does a single pass. Then it throws that away and does it again for the next token. So the ceiling is arithmetic you can do in your head. Tokens per second is roughly your memory bandwidth divided by the bytes you read per token. Real engines land between half and 3/4 of that. An 8 billion parameter model at 4-bit is about 5 GB. On that old card, 360 divided by 5 is 72. Measured, it does 55. 77% of the ceiling. Run the same model up the ladder and the line stays straight. A 3090, 936 GB a second, 115 tokens. A 5090, 1792, 200 tokens. Now take the card away entirely. Dual channel desktop memory runs about 96 GB a second, 18 times less than the top card. And that shows up as roughly 11 tokens a second on a 7 billion model. Apple sidesteps the whole argument by putting one pool of fast memory behind everything. An M5 Max moves 614 GB a second across 128 GB of it, which is how a Mac Studio ran a 671 billion parameter DeepSeek at around 17 tokens a second, pulling under 200 West, no rack, no cooling problem, no cloud. But bandwidth only governs half the work. Reading your prompt is a different job. That part happens in parallel, so it is bound by compute. Watch what that does to our 2 cards. At prompt processing, the newer, weaker card wins. 1,480 tokens a second against 1,119. Same 2 cards. Opposite answer. Paste huge prompts and you want compute. Chat and you want bandwidth. Which brings us to the second thing, and to the number people quote most, parameter count. On its own, it tells you close to nothing about speed. 1 graphics card, a 3090. Qwen 3 at 32 billion parameters, dense, 35 tokens a second. Qwen 3 at 30 billion parameters, mixture of experts, 153. 4.5 times faster on a model that is very slightly smaller, because a mixture of experts model does not read all of itself. A router wakes a handful of expert blocks per token, and the rest stays asleep. Alibaba ships 35 billion total with 3 billion awake. Google ships 26 billion with 3.8 awake, and says on the model card that it runs about as fast as a 4 billion model. The catch is that sleeping weights still take up room. That 35 billion model is 20 GB on your card, whether the experts fire or not. Sparsity buys you speed. It does not buy you space. You can see the ceiling that creates. Moonshot open-sourced Kimi K3 recently, 2.8 trillion parameters, 1.4 terabytes of weights, 6,800 likes on Hugging Face, 2,850 downloads. The parameter count is real. Nobody is running it. Third thing, and the one that costs people the most money. Does it fit? Miss the size of your card by 1 GB and you fall off a cliff. Someone benchmarked it properly on a 14 billion model. Everything on the processor, 2.9 tokens a second. Everything on the graphics card, 43, 15 times. Now the interesting part. Push 40 of the 48 layers onto the card and you get 12.5. 83% of the model on the GPU buys you 29% of the speed. The last 8 layers do the rest, which is why everybody quantizes. Full precision weights are 16 bits each. Quantizing rounds them down to 4 or 5 bits in small blocks, with a scale factor kept per block so the range survives. A 32 billion parameter model goes from 65.5 GB to under 20. That is the difference between renting a data center GPU and using a secondhand card in the machine you already own. The cost is usually described as a 1 to 3% quality loss, which is a generous way to put it. Measured against full precision on the same prompt, 4-bit picks a different next word 8% of the time. Down the ladder, 8-bit is effectively free, 6-bit is cheap, 4-bit is the knee, 3-bit does real damage. 1-bit turns a perplexity of 6 into a perplexity of 60. It is still talking. It has stopped thinking. The damage is not spread evenly either. Dropping to 3-bit cost one model 9 points on grade school maths and 0.6 of a point on common sense. Quantization eats reasoning first, and reasoning is usually why you came. Google trains for it now. Their quantization-aware checkpoints cut the 4-bit penalty by more than half and took a 27 billion model from 54 GB to 14. The community rule: pick a file 1 to 2 GB under your VRAM, and that rule is about to fail you, because the model file is not the thing that fills your card. Fourth thing, context, which is bigger than your model and which almost nobody accounts for before they download anything. Every token the model has already read leaves something behind. A key and a value per attention layer, cached so it never has to recompute them. That cache sits in your VRAM next to the weights and grows with every word. On an 8 billion model, it costs about 147 kilobytes per token. At 4,000 tokens of context, that is 0.6 of a gigabyte. Small enough to ignore. At 128,000 tokens, the same cache is 19 gigabytes. The model file is 5. Your context is now nearly 4 times bigger than your model, so the calculator you used before you downloaded anything was wrong. Weights plus cache plus a working buffer plus whatever your desktop already has sitting on the card. People shrink the cache the same way they shrink the weights. But this is where the tutorials go wrong, because keys and values are not equally fragile. Quantize the values to 4 bits, and the divergence from full precision is nearly nothing. Quantize the keys to 4 bits, and the model now agrees with its own full precision answers only 11% of the time. The reason is mechanical. Keys pass through a softmax, so an error at one position spreads across every position. Values just get added up, so their error stays put. 8-bit keys, 4-bit values, and you keep 60% of the memory. Architecture fixes it better than settings do. DeepSeek compresses the cache to 70 kilobytes a token instead of 300. Gemma alternates local and global attention and drops the cache from 60% of inference memory down to 15%. And now the part that should change what you buy. Somebody pushed 172 billion tokens through 35 open models at 32,000, 128,000, and 200,000 tokens of context. Median accuracy loss from 32 to 128,000 tokens, 10.5 points. One well-liked model fell from 93% to 37% at 200,000. Its invented answer rate went from 7% to 72%. Same study, same machines. 8-bit weights cost under 2 points. Context cost 20. The setting everyone argues about barely matters. The number in the marketing is the one that does. Fifth thing, and the one that decides whether you should do any of this at all. What are you running it for? Start by not agonizing over the app. For one person making one request at a time, llama.cpp, ollama, and LM Studio land within a few tokens a second of each other. vllm is much faster at serving 40 people at once, which you are not doing. 2 things did change this year. In February, the team behind llama.cpp joined Hugging Face. Georgy Gerganov wrote that local inference is becoming a competitive alternative to the cloud, and the way people deploy it has to get simpler. In March, Ollama swapped llama.cpp for Apple's MLX on Mac. Same machine, same model. Prompt processing up 57%, generation up 93%. A bigger jump than any card you could have bought that month. The chip underneath barely touches quality. Across an H200, an MI300X, and a Gaudi 2, accuracy on the same task varies by half a point. Temperature moved it up to 9 times more than the hardware did. Then there is the bill. OpenAI will sell you 1 million input tokens for 5 cents. DeepSeek will run a capable model for 14. Meanwhile, American electricity hit 18.5 cents a kilowatt hour, up 6% in a year. And the card got worse, not better. The 5090 carries a $2,000 sticker and sells for about $4,300 because the memory makers moved their lines to data center parts. The break-even people keep landing on. Under $50 a month of API spend, cloud wins outright. Above a few hundred a month sustained, the machine pays for itself inside half a year. The capability gap is real too. On the standard software engineering benchmark, the best closed model score is 89. The best open weights model score is 79, and that one wants a server, not a laptop. Agents are where you feel it most. Past roughly 25 to 30 tool calls, local models lose the thread. They forget early results, redo finished steps with a context window still half empty. So here is the yes. Local wins at small, repetitive, private, and constant. Classification, extraction, summarizing your own files, autocomplete, anything you would rather not paste into someone else's server. And it is not a hobby anymore. Ollama reports 8.9 million monthly developers, double January, running inside 85% of the Fortune 500 on a team of 14 people. OpenWeights took 41% of Hugging Face downloads this spring. On Vercel, open models handle close to a third of all AI requests in June, and the gap has a measurement now. The UK AI Security Institute put OpenWeights 4 to 7 months behind the closed frontier, narrowed from 6 to 10 months a year ago. Practically, 8 GB runs a 9 billion model at 4-bit with real context. 16 runs a 12 billion or a 26 billion sparse one. 24 runs a 27 billion coding model at 25 tokens a second on a laptop. 5 things. Bandwidth over compute. Bytes awake over parameters. Fit, with that cliff behind it. Context, which is bigger than your model. And the job, which decides all 4. Buy bandwidth. Count what is awake. Leave room for the cache. And be straight with yourself about the work. That is the checklist. Everything else is a preference.